So this talk is about visualizing Postgres performance, specifically focusing on I/O. And the story or the origin behind it was that I work at Microsoft now, working on Postgres. And when I joined, we were looking at how to make Postgres go faster in Azure. And so one of the things that we were looking into was how we could tune different kernel block device settings. And in order to do something like that at a cloud provider and actually roll it out for customers, you have to really test it and benchmark and make sure that the things that you're trying to do actually are a good idea and don't cause regressions and that kind of thing. So, one of the things we did was test all different instance types and different permanent storage types and different combinations of them and look at what type of settings would make sense. But that's in the cloud, and today I'm going to talk about just local storage because I wanted to, that was my first time doing I/O benchmarking. And so learning about it was a process, and then doing it locally was a whole new set of learnings, I felt like. So when you hear about performance numbers for databases, typically you'll see a lot of bar charts like this, which is total TPS. And it's this is faster than this. And so what I really wanted to focus on was the story of a benchmark. So what happens along a certain timeline, and looking at performance metrics over time, because the experience that the user has is going to be affected a lot by, latency. And looking at this chart, there's peaks and valleys and that kind of thing. So today what I'm going to do is talk about how do you find and understand the story of what those peaks and valleys are, kind of, if that makes sense. So I think right now, we don't have all of the information that you would need to figure out what something like one of those little peaks is just in Postgres statistics. So I used multiple different systems and tools to gather information. So in the storage stack, we have the file system, we have the kernel page cache, we have these different layers, and getting information about what's happening with I/O at those different, I think this is old because that doesn't even have block MQ in it, but whatever, you get the idea. And so getting an idea of what's happening at each level, you can use different tools for that. So for the purposes of this presentation, the benchmarks I'm going to talk about, these are the sources that I used. So I used pgstat.io, which is a view in Postgres. I used pgbuffercache. Well, that's actually not syntactically correct. But anyway, I used pgbuffercache summary, and I used statistics from pgstat-wall. I used wait events from pgstat-activity, and I plot pg total relation size over time. At the operating system level, I didn't put IOStat. That's the most important one. So IOStat, I used IOStat, and watch of proc mem-info, and then PIDstat of the checkpointer process. And then today I'm just showing pgbench benchmarks, but that's not because it just basically was easiest for the purposes of the presentation. So, and just this was my setup. I'm not going to read it off to you, but it's in case you want it. So using metrics together to understand the why. So the first scenario, I'm going to go through a series of scenarios. The first has to do with backend flush after. And I was worried that these wouldn't be big enough to see. So I'll verbally describe to you what you can see here. So this was pgbench with a custom file, so not one of the built-in scripts, doing a copy with 16 clients of a 10 MB file. And pgbench you can either run for a certain amount of time or for a certain number of transactions. And so in this case, I picked 700 transactions, and I have shared buffers set to 20 gigs. So what you'll notice is, so the orange are the top line. So this is cumulative transactions per second. And you have more cumulative transactions per second with backend flush after set to 1 meg. And so I wanted to, this is a specific scenario. Of course, you can devise scenarios where this isn't true. I'm not saying you should always set backend flush after to that. But I wanted to talk about how to understand why this is. So backend flush after is a GUC that allows you to basically tell backends that after they've written a certain amount, or dirtied a certain amount of data, that they can do essentially a sync file range. It's different on different operating systems, but you tell them they can advise the kernel basically to flush out the dirty data. And the idea behind it is that you're going to sort of even out the amount of writing that the kernel is doing out so that you don't see sudden spikes and increased write latency, which affects the experience that the user has, right? So here you can see this is the non-cumulative TPS, so just the TPS at the top. And then on the bottom, you can see backend writeback. So this is from pgstat.io. And with backend flush after set, of course, you have way more writebacks. And that's advising the kernel, hey, please flush this data. I wanted to get into sort of like a little bit deeper on what that actually means. So the other chart you can see, the top is latency, pgbench latency. And see, like, it's super spiky. Actually looks like some kind of art. But so without backend flush after, we have large latency spikes. And those pretty much line up exactly with, this is from IOStat. So IOStat has a statistic called average queue size, which is exactly what it sounds like. But it's looking at that at the kernel level as opposed to the application level. And it's not the device level either. So you can see that actually we get a spike in latency when the queue has more requests in it. So those are probably related. I mean, all of this is inference, and obviously I can't prove it unless I got out like block trace or something. But so those look like they kind of line up, right? So possibly what we kind of can understand from this, and I mean, I think you could look at the first graph and say, oh yeah, well, obviously it's better to have backend flush after, but the whole point of spending the time to look at this and understand what the system is doing is so that when you set backend flush after and it makes performance worse, you're not just like, oh, I don't know, I guess I'll just keep changing it and see what happens. Like, the idea is to understand what the system is actually doing. So this is from procmem.info, dirty KB at the bottom. And that is, I mean, pretty much the obvious consequence of what we did, which is you have a bunch more dirty data, and that's building up when you don't have backend flush after set. So when it's tested 0, the backends will never themselves do a system call to advise the kernel to write out dirty data. So you're getting more dirty data building up. And so what I also wanted to do, this is kind of like switching gears, but with the same benchmark runs with the same settings, is talk about dips. So before I just, like, at a high level talked about what do we see as a trend over the benchmark run. But here I wanted to talk about, like, okay, great, with backend flush after, the performance, the TPS seem better, but there's still some dips and some things in the chart that are unexplained, right? So the initial performance at the very beginning is like pretty consistent, pretty good. And then we start to see it sort of spread out. And before 200 seconds, so starting at the beginning, that initial piece lines up with when free memory from procmem.info gets to 0. So of course, like, when the system doesn't have free memory anymore, performance is going to start to get worse, right? Because we have to get things from the device, the storage. And the second dip is like the dip that we all see when we look at benchmarks. It's checkpointer, our old friend. So that really coincides with that. And I have checkpoint timeout set to 3 minutes instead of the default to kind of allow me to see more checkpoints during the benchmark. So using metrics to clarify other metrics, which I guess we kind of are already doing, but let's I'm taking an example of wall compression. So wall compression you can set it to LZ4 or Z standard or PGLZ, I think. These benchmark runs are it's set to Z standard, and it does kind of what it sounds like. It compresses here full page images from full page writes, and in some cases improves performance. So this is the orange line is with compression, with wall compression. And the blue line, the bottom line, is without, with the default, which is nothing. And these charts are auto-generated, so apologies if they're kind of hard to read. But so you can see that the cumulative TPS is higher when we have wall compression enabled. In this example, I did TPCB like the built-in sort of default pgbench workload. The default ones are, there's a select only, there's a simple update, and there's just like one that sort of imitates the TPCB. It's essentially a couple inserts, an update, a select, with query mode prepared. And the data scale is 4,000 on my machine. This was, the workload was like a little bit smaller than memory, or it looks like it was, but it's actually bigger because of double buffering. So, you know, it's going to, at some point during the benchmark, start to slow down because of you're going to be going to disk. It was with 16 clients, and I did it for time instead of for transactions, and set shared buffers to 20 gigs also. So you see that in the first example is our non-cumulative TPS, or regular TPS chart. And the TPS is, like we looked at before, is higher with compression, and it's also consistent. It's not as spiky. Those icicles aren't there for when we're using compression. And the latency kind of matches up exactly, which makes sense with the TPS. And overall, we have, because I did it for time instead of a number of transactions, like we're processing more transactions in the case with the compression, which seems obvious, but will become important in a second. So of course, this is from PG stat wall, PG wall stat. It's the number of full page images. So you can see that with compression, we're actually doing more FPIs, but that's because we're like doing more transactions. So that makes sense, right? And interestingly, so without compression, we're doing fewer writes per second. So that kind of makes sense because we're doing less transactions, but it makes less sense when you think about the fact that we have to write more wall. This is from IOstat, so this is how many writes per second the system is doing. So why are we doing less if we're writing more? And the reason is because it's throughput. So we're doing larger writes and fewer of them a second. So that is, we're basically, most of our writes are being dedicated to writing wall. So our write throughput is higher. And in PGStat wall, you can also see the wall bytes. So without compression, there are more of them because we're writing more wall. And again, this is wall syncs from PGStat wall, and this is flush requests from IOstat. And so we're doing more wall syncs and more flush requests without wall compression. And so kind of the point that I was trying to make is that you can use these other tools. Like you can start with a hypothesis or a conclusion and say, okay, I'm doing more full page writes, so like it's gonna write more. But I think actually looking at what you can get from the system and understanding exactly what's happening is more useful than just assuming. And so separating out, okay, of my total write throughput, how much of it is wall and how much of it is backend reading and writing data, and kind of like understanding the proportion there. So this is from PGStat.io also, and this is backends doing writes on the top and backends doing reads on the bottom. And so with wall compression, we're doing more data reads and writes. Sorry, this is backends reads and writes of data, like from relations. So we're doing more of that and less of our I/O as well. So we're dedicating time to something that's, well, not more useful, but we're spending more time actually. That's why we get more transactions done. So, okay, so I just wanted to talk a little bit about some interesting things around benchmarking setup. So this is I'm not saying you should initDB before every benchmark, but I'm going to explain why it matters whether or not you do that. So this benchmark is pgbench 16 clients doing a 1 meg file. So one of the previous ones was 10 and 20, but this one's 1, so it's a smaller file. And I had pgbench do 2,000 transactions. So you can tell when something finishes sooner, it's finished doing 2,000 of those. So with in the green line is that we did not do initDB. So like the way I would do the run is I have script and it does either does initDB or doesn't, and then it creates a database and loads data into it and goes through all these steps. So in the blue line, I did that. I did initdb and then all those steps. And the green line, I just dropped and recreated the database and loaded data into it for the benchmark. And so you can see it's much faster when we haven't done initdb. So does anyone know why? This one's fun. No? Okay. Well, also I hate when people ask interactive questions of the audience. I'm really sorry I did that. Ugh, gross. Okay, so anyway, this is from IOStat. It's flush requests per second. So if you notice, when we did initdb, we're making way more flush requests. So that's interesting, like consistently, except for at the very beginning. And then this is wait events, right? So I guess I learned about this the other day, so I actually didn't know this until recently, but when we have to make a new wall file, the process of doing that takes time because we have to, first of all, we actually have to fill the file with zeros, and then we end up syncing it. So when you've just done initdb and you don't have any wall files and they're allocated and initialized lazily, there's a cost each time that you need to do that. And so you'll notice that in your wait events and you'll notice it in your overall performance. So this is when we actually did do initdb before and we have some wall init sync wait events. And so this is kind of unrelated to that, but I just thought I think it's interesting to figure out, okay, what is this dip in this particular place? So if you see at 40 seconds, we have a dip that corresponds exactly with the mem-free KB from proc mem-info. So we actually basically it's a pretty big dip, right? So we finish quickly, but at 40 seconds, all of a sudden it craters. So that is exactly when we ran out of memory, so it kind of makes sense, right? So as a twist on this, I also did the same benchmark, but I used a larger wall segment size. So the files for wall by default are 16 MB, and you can configure them to be larger. So I configured them to be 1 gig. And so the interesting thing here is, so the blue, the orange and the red lines are with the larger walls. Yeah, okay, this is impossible to see. This is my first time doing this presentation, and now I know that visually it's very difficult to read. So yeah, the orange and the red line are with the larger wall segment size. The green and the blue are with the smaller one. And then, so the red line that we're all noticing is we did initdb with the 1 gig wall segment size. So it's super spiky. And this was cumulative TPS. So with the larger wall segment size, it takes longer to copy the 2,000 times of copying that file. And this is from IOStat. This is flushes per second. So I didn't put it on there, but if you look back, those spikes pretty much line up exactly with this. And the other thing I wanted to point out is that if you notice in the red line, right? So with the larger wall segment size, it goes down, but when it is at its peak, you actually do have higher TPS than you did with the smaller wall segment size. So you have lower lows and higher highs. So it's not like, oh, well, obviously some people want larger wall segment sizes. There are benefits to it, but I'm just showing it, I'm exercising a case where the overall performance impact is probably negative, but there's times where it's actually much higher TPS. So each flush request is going to be synchronous and is going to take longer if more data has to be flushed, and then you're waiting for that to happen. So that is what you're kind of seeing with the flush requests there and why they're spread apart. And I assume also some of this time is doing the allocation of the wall file and filling it with zeros, but I don't know. Something that's interesting is that there's min wall size and max wall size that you can configure. And if min wall size is less than max wall size, then after a checkpoint, you will remove, you could remove files instead of recycling them. Typically, you would reuse wall that the checkpoint, after the checkpoint, you're allowed to get rid of it. So instead of getting rid of it, you reuse it because it can be expensive to and the reason to get rid of it is that maybe you want that disk space back. So in this example, I decreased, for all the previous examples, min wall size and max wall size were the same. But in this example, I decreased min wall size, and then after doing create DB and loading the data before running the benchmark, I paused for enough time, that basically longer than checkpoint timeout, and the result of that was that actually doing initDB before the benchmark and not doing it but pausing have roughly the same performance. And the number of flush requests is the same also, so that makes sense. And we see more of these weights, again, with the pause and the decreased min wall size. So when you're choosing your benchmark configuration, so of course I said today I'm only talking about when you use PGBench, so I'll just go over some options there. Obviously, if you're implementing one of the TPCs, there's a lot of other choices. So a quick one is prepared query mode versus simple. And I think this varies a lot, but this is like sort of the basic example. It's TPCB with a workload that is less than the size of memory. Your working set is less than the size of memory. And so you see you have higher TPS with prepared query mode. And this is from IOStat. So this is CPU in user space. So what CPUs, and that is higher with simple because the parsing and planning overhead and that kind of thing you're not incurring them with prepared query mode. And the next one is about what benchmark you decide to do. So I've given examples where you do a custom file with copy with PGBench and built-in TPCB. And one of the criticisms of these workloads is that they don't represent real customer workloads because they uniformly access data, basically all of the data. So in PGBench, you can choose to use different functions that let you do different kinds of data access patterns. So one of them is Gaussian, and you can pick basically what the distribution looks like and how much of your data you actually access. And so this one is the custom one. I used the Gaussian weight of 9, so I tried to make it as narrow as possible, like the number of buffers that would be accessed, or the number of blocks in the number of blocks in the file. And these results are more dramatic because synchronous commit is off, but I think the point still stands. So data scale is going to be a little bit bigger than memory, but close. And there's 16 clients. I ran it for time, not for transactions. So this is for 500 seconds. And I think this is exactly the kind of thing we're expecting to see, right? Which is that less stuff is going in to needing to be read in and unmodified out of your files, so it'll be faster, and you'll do less I/O. So on the top is read throughput, and the bottom is write throughput, and you can see that with the random uniform access, you end up doing a lot more reads and a lot more writes. And this one's cool. So this is from PG Buffer Cache, and the bottom is the uniform random access, and the top is with the Gaussian distribution. And the usage count stays low because people are like there's more blocks getting read into shared buffers, and there's more demand for them, and so backends are going around the free list and are going around and looking for other blocks that they can evict from buffers so that they can then use them, and decreasing the usage count as they do that. And then this is calculated from pg.io also. So this is the cache hit ratio for normal backends reading data. And I think this is like directly sort of evidence of, okay, you have a smaller working set, so your cache hit ratio will be better. And then, of course, you have more evictions of shared buffers, which is also, this is from PG.io, also with random access, uniform access. And backends themselves are doing more reads and writes. So that also is sort of reinforcing the same point. So next I wanted to talk about system configuration. So at the beginning, I mentioned that I had done some work with Linux kernel block device settings. And so I just wanted to talk about one of them. What I found was that a lot of them make less of a difference when you're using a local SSD that's fast to do benchmarking than it would in the cloud or somewhere where you have increased latency. So I'm just going to talk about read ahead. So read ahead is how basically the kernel, well, in this context, the kernel is going to read ahead some amount of data to try to make sure that it can cover up the latency of going to disk so that when you need a block, it's already in the kernel buffer cache. And so, I mean, this formula is coarse, but the idea is that if you have very low latency and you multiply it by bandwidth, then you're going to get a small-ish number, because like you're basically dividing, because it would be really like a fraction of a second. So if you have whatever 700 nanoseconds, microsecond latency, probably not nanoseconds, microsecond latency, that you're not going to need to set read ahead very high to be able to make sure that when you need a block, it's available in the kernel buffer cache. So this is on the same benchmarking setup, the same system as all my other results. And this is pgbench with a custom workload that's a little bit different. So it's just select star from a 5 gig table. One client, and I do it 3 times, I mean, I could have just done it once, but whatever. And 8 shared buffers, 8 gigs. So when the default read ahead on my local SSD with whatever else is going on my setup was 128K. And so that is the orange line. And the green line is with it set to, I guess, 2 MB, or bigger, yeah. And it with 128K, it takes a little bit longer to finish. So this was a fixed number of transactions. So if it takes less time, then that's better. But it's not better enough to really matter, right? Like, who cares? So, but we can still see some of the same effects. So we see that the average read request size is larger. This is from IOStat. It's the average read request size. And what that means is, even though we're leveraging the larger read ahead value and the kernel is saying, okay, sure, I'll go out and get more, your storage latency is so low that it doesn't really matter. But if your storage latency is higher, then like a larger read ahead value makes a big difference in your experience of the performance. So this is an example using DM setup and adding a delay to the storage. And this is with a delay of 1 millisecond. And for reference, like a lot of cloud permanent storage, non-ephemeral storage is going to have latency like 1, 2, 3 milliseconds. So in this case, the green line, that's 25 seconds in, it like finishes, it's done. So that's way faster. That makes a difference, right? And again, the average read request size is larger and our read throughput is higher. Oh, well, I thought there was one in here about why, yeah, queue size. But anyway, so we're basically, I mean, the same thing's happening in your local storage. You're doing more read ahead, but it just matters more because your latency is higher. So next I wanted to talk about questioning assumptions that we have about what we think we know about different parameters and what they do. So, or not what they do, but what their effect would be. So this is an example with auto vacuum cost delay. And so the setup is kind of fancy. It's a TPCB, like, the built-in script at wait 1, and then an insert and delete. So I made a table that had some amount of data in it, and then I'm doing an insert and a delete on that table. I'm not deleting all of the data I added, but much of it, and that's at wait 9. So the waits in pgbench let you say I think it's like how likely it is to be picked, but I haven't looked at that code, so 9 seemed bigger than 1. But anyway, and so this data scale is pretty large with 32 clients, and I ran it for time for 600 seconds. And so the blue line is the default auto vacuum cost delay, and Green is with it set to 0. And the orange is just for fun. No one's probably setting their auto vacuum cost delay to 100, but if you are, it's not a good idea. And so what you can see, or I guess previously the TPS was highest with auto vacuum cost delay set to 0. And this particular chart I think is really interesting. So with the auto vacuum cost delay set to 100, latency just like keeps going up, sort of an uncontrolled pace, it feels like. I mean, it looks like a bigger increase than the lack of TPS, but I guess it's still diverging at the same rate. So the thing that I thought was interesting is that I assumed that I didn't really think about the fact that we would be doing less I/O overall with our auto vacuum cost delay set higher, because like, you know, maybe auto vacuum will run less, but like the backends can do what they were doing normally, right? Or do more I/O if there's auto vacuum's not running. But you actually see, so IOStat util is the device utilization, and that's like basically, it doesn't mean the device is saturated if it's at 100, but it's just by comparing them, like with auto vacuum cost delay set to 0 or 2 milliseconds, the device is being utilized more. And so I think the thing that's interesting is that a lot of times people think that when you see issues and auto vacuum's not working correctly, it's because it's not keeping up with, not able to keep up with the rate at which you're inserting and deleting data or whatever. But in some cases, based on this setting, it's actually just waiting. So this is the vacuum delay wait event. And it's pretty similar with 100 milliseconds and 2 milliseconds. I mean, not that similar, but it's still 2 milliseconds is not really short enough to avoid having the vacuum delay wait almost the whole time, or second half. And so we have reads up here. This is with the auto vacuum cost delay set to 100. So we see some reads, and it's like, I wonder what those are. And then this is from PGCon. It's auto vacuum reads. And so, of course, it's waiting. It's not doing anything, so it's not doing reads. And this is the total relation size. So you can see that the relation is getting, on the top, is getting much bigger when we're not vacuuming it frequently enough, which makes sense. And as that's happening, the backend's cache hit ratio for normal relation data is going down. And it kind of feels like it's going down at a rate that's like it's getting worse over time. And something that I noticed that I thought was interesting is that the system CPU usage was going up a lot and the user space CPU usage was going down a lot. And this is something that I threw in here because I'm not sure I still totally understand why that would be, because I see other cases where there's swapping and the system CPU usage is not going up. But I don't know, I didn't have a point here, I just thought this was interesting and I don't know how to explain it. So now, because we said, okay, people won't really set auto vacuum cost delay to 100, this is with just the default versus 0. And that's the latency. And you can see that the latency starts to get quite high. I mean, this is in milliseconds, so 120 milliseconds. Yes?
Is this kind of a situation where the real world versus like PGCon might be a bit different because, well, depending on your system in the real world, you might have like big parts that you like you're not going to be counting.
Yes, all of these are like this. But the part of I'll get to like what my point is, because who's running a workload at full bore all the time, right? This talk is meant for, I guess the idea is that as a developer, how can you use benchmarks to identify like how things work in the system? And if you pull here, this moves. As we start to identify performance bottlenecks, how do we know what the right thing is to fix? Not necessarily to replicate like a real user workload, but yes, that's a good point. Yes. Yeah. Sure.
Yeah, because I know it's kind of a problem with the main point. I was just like auto vacuum cost delay set to 0. In the real world, I've seen some big painful effects from. So
yeah.
It's kind of an interesting case where, like, I guess it's always hard to make a benchmark that actually happens.
Right. And I didn't really try to make a benchmark that matches reality. I think if there's anything I want you to take away from this is don't take configuration advice from this presentation. It's more that I wanted to sort of find examples that exercised the different metrics and system settings that then you could say, hey, I know what auto vacuum cost delay is. And so that's like interesting that I can see that. And then if you are trying to do something for a user and like replicates a real user workload, you can do that, make that, and then you'll know how to use these other tools. That's kind of was the idea. And then, yeah, so the relation size stays relatively consistent with it set to 0. And then this was just that there's more, the auto vacuum has more cache hits, so it's finding the things that it's vacuuming in shared buffers more. And yeah, and more evictions, more of the same. Oh, this one was interesting. So this is from PG buffer cache, and it's the unused buffers. So like the cool thing is that because vacuum's running, it's cleaning buffers and putting them back on the free list, which is nice. And yeah, it's kind of cool because you actually get to like 0. Yeah. And that means that backends don't have to flush dirty data when they need a new shared buffer, which is sort of the ideal, right? Oops. Okay, so I think I have 10 minutes left. This is probably my last example. So this one is about wall buffers. So this is a 20 MB file and 16 clients, again, doing 100 transactions, so not for time, but for a number of transactions. And I have the wall buffers set to 2 MB. Actually, those are the number of buffers, not the size, so I don't actually know what that translates to. But bigger, medium, and small, let's say that. And so I have this 1 gig and 128K, yeah, and 2 MB. So with the largest setting, with wall buffer set to 1 gig, the copies finish fastest. So this is from PGStat wall. This is wall buffers full, and so when we have a smaller wall buffer setting, we fill it up faster. So that's what that says. But I think this was interesting and something that I don't know a lot about this particular part of the subsystem, but this was something I noticed. So in the results, so with the smaller wall buffer settings, the type of weighting on the type of weights are different. So this is weighting on the wall insertion lightweight block. And so with the larger wall buffers, we're not really doing that as much. And with the smaller ones, we are. So anytime they need to put anything in wall buffers, there's a lot of weighting, as opposed to just at the time that they commit. So they're going to end up writing the files more slowly because throughout doing the copy, they're having to wait more often, I think. Yes, Andres. How many what? 16. Yeah, that's why I know I wouldn't include it, but it's 10 and 10, so I feel like 10 out of 16. I don't know, it's not nothing. Is it nothing? Yeah. Yeah, and then in the bottom, we even with large wall buffers, when you commit, you're going to have some amount of waiting to actually do the wall right. So I guess the thing that I thought was interesting is that you're doing less I/O because you're waiting more. And so the thing that's actually affecting your performance is contention and waiting, and not like, I guess I kind of thought it would be more like, I didn't know where the bottleneck would be, I guess. So I thought that was interesting. So this is from IOStat, and you can see with the smaller wall buffer settings, the device utilization is pretty low, and the number of fsyncs is way lower. Or that flush requests, I guess, not fsyncs. And then when we fill up wall buffers more, like if we fill it up more quickly and then we're having to do more syncs, then we're going to be waiting for the sync more often. So basically our I/O is getting spread out and being done more over time. So the next thing that I wanted to do with the same benchmark is actually talk about the peaks and valleys, because I think this one is particularly interesting. So with the larger wall buffer setting, you see the place where the TPS is sort of the highest, that one plateau, that corresponds with us having really high write throughput. So we're writing out all those files super quickly and a lot at once. But then there's this sort of decline, and I wanted to talk about what that could be caused by. So at 20 seconds, we start doing more smaller writes. So this is writes per second and write throughput. So that dip is like we have less writes, and the writes are, we start doing more writes, but they're smaller writes. And we're doing, this is from IOStat, it's the write requests merged. And so like that craters, we have way fewer write requests being merged. And because we have more requests, the average queue size goes up. There's more things in the queue. And so dirty data has built up, and then it starts being flushed by the kernel. And so the second slowdown sort of corresponds with, we can see that the dirty data has built up, and then it goes down. So the top is dirty KB from procmem info, and it goes down. And that kind of corresponds with when the second dip, so like that one, it corresponds with, okay, the kernel has been flushing out dirty data, so we start to slow down. And this is interesting. So this is buffers unused from PG buffer cache. And so around 20 seconds, we basically, with the large wall buffer setting, we basically filled up shared buffers. There's nothing unused. And then, as makes sense, backends suddenly have to do more writes because they have to flush dirty data themselves. And then around 30 to 40 seconds, system, this is free memory on the system, basically is used up. So you can kind of look at that and line it up with the actual TPS to try to explain it. And this is reads per second. So once backends are, so this was a copy example, right? I said, yeah. So it's kind of weird, like what things are you reading? And so I think you're doing some reads, I guess, of indexes, and but you don't. It looks like things are getting swapped out, and then you're having to read them back in. Is my interpretation of this, because it seems like there are less reads in the cases where wall buffers are smaller. So I assume that they're not like required reads. So I thought this was kind of interesting. So something is having to be read back in, and there's more of that happening when wall buffers is bigger. So again, back to kind of James's point, like this is not necessarily relevant for all workloads, or maybe representative of is typical customer workload, but if you're doing a transactional workload, you're not going to necessarily see a difference in changing wall buffers because the commits are flushing the wall themselves because they're committing. So I think something that's interesting and something that was a learning process for me a lot was like I would change a bunch of stuff because I was like, oh, maybe this will have an effect, and then nothing looks different, right? And so you really have to design the workload and at every level, from kernel settings to like every level, something like CPU performance, like frequency governor, like every level of the stack, you have to design to try to actually test the thing you're testing. Your PG bench configuration, your size of shared buffers, and like getting all of those pieces right so that you can try to exercise what you want to exercise is something that we have to do as developers. And that's kind of my point, is not that there's this great configuration that I can tell you to do for your database, but that as Postgres hackers, like how do we test the patches that we're writing for IO performance and actually test the thing we're trying to test? And when we're designing performance improvements, like how do we make sure that we understand the way the system is interacting with those changes? Yeah, that's it. Does anyone have questions?
It's not just testing it when we are developing it. It needs to be re-evaluated completely. This auto-make-queue delay feature, for example, a very old feature that came originally with Ladybug for the normal one. And the design behind it was that out of vacuum would not IO star an application that does not fit into shared buffers or memory. And I think the world has changed now. Yeah, first of all, out of vacuum puts things, as you said, onto the free list. Back then, it didn't do that. So that changes the whole way it interacts with the remaining application. Therefore, we need to reevaluate those things.
I don't think automatic puts it's on the free list.
But I didn't know that either.
So,
I thought it did, no?
I mean, a tiny amount.
But I think what she was showing was that it just wasn't keeping up it, keeping the table questions.
Yeah, that too.
Maybe what we really needed something that auto-adjusts the vacuum delay based
Right.
on keeping up.
Why would buffers unused go like up then? Or buffers used go down in PG buffer cache if it's not putting things on the free list?
Probably you could win into truncate the relation.
Oh.
Or a vacuum, right?
Yeah.
Yeah, but it sounds like the normal specific part at the end, like truncate the relation.
Okay.
It's still very much possible to star IO on the application.
Oh, yeah.
But that basically means you need to have something more adaptive than truncate configuration IO. You have to use like the math that's wrong to figure out what the standard is. That's kind of useless. Yeah, so it occurs to me that you're making the point that it's important to account for the way in which she's setting what these mechanisms can individually interact with the serial audio. But it occurs to me that it might be that the problem is in fact that they interact when in principle it could be avoided. I wonder if you see an opportunity to do that in a sort of context where, yes, two things are adapting very wonderful ways, which isn't a problem with what you're doing or what you're trying to do, but rather the problem with the things themselves. To improvement. Have you ever
Hmm.
I can think of a lot of things like that with batteries in particular, where it's like they do one thing and it just they interact in ways that don't make any sense at all. And the problem is that, or as I said, not that you have to be careful, but also looking at the problem separately.
Right.
So like separately from understanding that
Yeah. I think that's a good point. I think I don't have a specific example, but I take your point. Yeah. Any other questions? Okay. Cool. Oh, yeah.
How long did all the tests you took and how many machines?
Well, I just did it on my local workstation. And a lot of the runs were pretty short, but I ran them many times because, of course, there's run variants. And I think the harder part is seeing unexpected things and then trying to figure out what they are. So like the total amount of time represented up here is probably like, I don't know, 10 minutes or something, but that's way less than the time I spent on doing these benchmarks. So yeah.
I have like this application code that's issuing quite large complex queries, and like I'll find that sort of between runs, like the database kind of warms up, and we'll I think have some of that data cached and do various optimizations, and it makes it harder to sort of profile the queries and to try to optimize them. Is there a way to sort of tell Postgres to reset that, like basically tell it, go back to the state you were in when you first turned on, and then I'll try to code to see how long it takes to run the queries. And then
Well, you could use
sort of tinker with them. And
PG pre-warm, I guess, but that's all I can think of.
I'm just seeing like I can tell it's doing things anticipating that query,
Mm-hmm.
and because I'm doing these kind of quite large queries where like I think if it was a lot of smaller queries, I could kind of like randomize them more to prevent the database from just learning the particular thing I was asking for. Here I'm using a sizable fraction of the data in the database.
Okay.
And I just kind of need some way to, reset it. And I think also it's sort of, at the OS level, it's caching some of the data that's needed.
Well, you can drop the OS caches if you want to replicate sort of having a totally cold cache. But in terms of getting it to a specific state at a point in your workload, I don't know how you would do that, actually. I don't know if anyone else does. Yeah.
That's the way to go.
Yeah, well, no, I mean, so originally I was hoping to have the tool in a place where people could use it, but now it's full of dirty hacks that I use to get done with this. But so I just use like a bash script to actually, run pgbench and get all that like procmem info and all that. And what if I've learned anything working with Postgres developers is that no one will ever use the tools you make. They're going to run pgbench how they're going to run pgbench, and that's it. But I did make a separate tool that's just about rendering. And so the idea behind it is that if I do, because I've tried all these different configurations, right? And so it makes a tree based on the metadata and groups it. And so I give it includes and excludes, and basically everything gets put into a JSON, all of the metadata. I get information from file system, everything, like every piece of metadata that I can about the disk and the CPU and everything. And then when I want to look at runs plotted against each other, it does grouping of the metadata, and then I can mask certain parts of it out. And so then you only see data charted together that is actually comparable in the way that you want it to be. And that I would like to share at some point because I think it's pretty useful. And it doesn't make any assumptions about what kind of data or how you generate it, or you can use your own pgbench tool, like runner script thing. All you need is to tell it what the timeline key is, and it will like chart it. But right. Yeah, and it lines them all up. So you see IO stat and TPA, like everything is completely lined up. Anyone who's interested, I can show you. It's like an IPython notebook at the end. I'd look at it. But yeah. Yeah. Yeah, I mean, Andres wrote a tool that is, I don't know if it's like ready for prime time, but that does some of that, and I based some of the ideas off of it, but the actual renderer, I wanted it to be like totally separate from everything, and it's basically just about grouping metadata. Because one of the problems I have when you do hundreds of different benchmarks is that it was really hard to figure out, okay, what should I chart together, because I don't remember if these things actually are comparable at all. Like you don't want to compare something that was run on a VM like in the cloud to something you ran on your local SSD. Well, maybe you do, but you want to be specific about that. Yeah, I use matplotlib and pandas, to actually do that. I didn't do any of the like making visual stuff. It's just about the grouping logic. Yeah. Cool. Thank you.